Καλησπέρα κυρίες και κύριοι. Όπως ίσως έχετε ενημερωθεί, η απόψινή βραδιά, η συζήτηση και οι ομιλίες θα γίνουν στα αγγλικά, οπότε θα ξεκινήσουμε ευθύς αμέσως. On behalf of Eugenides Foundation and ROPI Publishers, I welcome you to this special event. It's a great honor and pleasure to present Professor Kip Thorne, one of the greatest living theoretical physicists, Nobel laureate, one of the world's leading experts on the astrophysical implications of Einstein's general theory of relativity. If I say something wrong, you can correct me.
Yeah, this is all wrong.
This is all wrong? Yeah. Okay. So how should we...
The world thinks
I'm much better than I really am.
All right. As you know, in 2017, Kip Thorne was awarded the Nobel Prize in Physics, along with Rainer Weiss and Baris, for decisive contributions to the LIGO detector and the observation of gravitational waves. Very briefly, Kip Thorne became one of the youngest full professors in the history of the California Institute of Technology at the age of 30. He became an associate professor in 1967 at Caltech, California Institute of Technology, and became a professor of theoretical physics in 1970, and the Feynman Professor of Theoretical Physics in 1991. He is now the Feynman Emeritus Professor of Theoretical Physics. Throughout the years, Professor Thorne has served as a mentor and thesis advisor for many leading theorists who now work on observational, experimental, or astrophysical aspects of general relativity. Approximately 50 physicists have received PhDs at Caltech under Thorne's personal mentorship. One of them is here tonight with us, Haris Apostolatos, to whom I will give, he'll speak later on. Thorne's research has principally focused on relativistic astrophysics and gravitation physics, with emphasis on relativistic stars, black holes, and especially gravitational waves. He's perhaps best known to the public for his controversial theory that wormholes can conceivably be used for time travel. Was that controversial, really?
I'm sorry. It's still controversial.
Okay.
and it should be.
Okay, then. In 1994, Professor Thorne published Black Holes and Time Warps, Einstein's Outrageous Legacy. Personally, this is one of my favorite books. It's a book for non-scientists, for which he received numerous awards. This book has been published in 6 languages. I think there are more than that. This is also wrong. There are editions in Chinese, Italian, Czech, Polish, and also Greek. And one of the translators was Haris Apostolatos. Thorne contributed ideas on wormhole travel to Carl Sagan for use in his novel Contact. Initially, Carl Sagan wanted to put his main character into a black hole, and Professor Thorne prevented that from happening because she would get killed, apparently. In contrast to Matthew McConaughey. Thorne and his friend, producer Linda Obst, also developed the concept for the Christopher Nolan film Interstellar. And he also wrote a tie-in book, The Science of Interstellar, which is also published in Greek by ROPI Publishers. ROPI is one great publishing house from Thessaloniki, focusing on science and popular science. And Panos Charitos, the publisher, we should thank him for making this happen, and also along with the Eugenides Foundation for this event to happen tonight. Professor Thorne has also somehow participated in popular culture because he is portrayed in The Theory of Everything by an actor. And also, he himself appeared in one of the episodes of The Big Bang Theory. I missed that, and I regret it till today. Right now, we're in a time after the detection of gravitational waves and after the presentation of the first ever image of a black hole. It seems that as we're getting into the 21st century, we're entering a great age, a great era in terms of astrophysics and cosmology. So this is a great opportunity for us, once in a lifetime, to have someone like Kip Thorne here in Athens tonight. I'm not going to say anything more. I'll pass it over to Professor Haris Apostolatos, Professor of Physics at University of Athens, and one of Kip Thorne's many students.
And change the slides. So, first of all, let me thank Eugenides Foundation, which organized this great event, this great Athenian event. I would like to thank Panos Charitos, an astrophysicist, among other things, who published this nice book of Kip Thorne's, The Science of Interstellar. Actually, it was Panos' idea to bring Kip Thorne in Athens and tomorrow in Thessaloniki to talk to the enthusiastic Greek audience. The event has also been supported by the vigorous Hellenic Society of Relativity, Gravitational and Cosmology, counting a lot of young Greek students and researchers today. Can I have the blackboard, please? So, I am Theocharis Apostolatos. Next to me is sitting Kip Thorne. Happens to be a Nobel laureate, and next to him we have Elias Magdalidis. Right. And we have this enthusiastic audience. This was the usual beginning of the weekly ceremony in Caltech when our mentor, Kip Thorne, was introducing to us, the members of his international group of graduate students and postdocs, his distinguished visitors. The introduction and the discussion following it was very informal, whether the visitor was Stephen Hawking, Richard Feynman, John Wheeler, Dimitris Christodoulou, or Albert Einstein himself. To give you a taste of the atmosphere, can we take the blackboard back? To give you a taste of the atmosphere, this is the blackboard, I think, at the interaction room down the hall of Bridge Annex building, just a few steps of Kip's office, where the introduction and the long discussion following it was taking place. Each one of us had to explain the project he was struggling with and present his weekly progress to the rest attendees. For me, the whole experience at Caltech was an extraordinary experience. Not only the group meetings. From the first moment I met Kip Thorne, I was fascinated. Actually, I came to Caltech to do my PhD in some theoretical field, probably elementary particle physics. However, Kip's unique pictorial way to talk about physics while teaching general relativity and classical mechanics was intoxicating. Quickly, I was converted to a fanatic follower of geometry dynamics. Kip had a very special relation with his students. He was caring for them a lot, and he was very supportive. Actually, I cannot imagine a PhD supervisor more devoted to his students. We, his students, had the feeling that we were his first priority, even more than his own research projects. In retrospect, I cannot explain how had he managed to push forward his vision about constructing these wonderful devices, gravitational wave detectors, and persuade numerous committees to proceed in financing them, while he was spending infinite amount of time discussing with us, both collectively and face-to-face, checking and correcting every single detail in our paper. This is a common example of Kip's endless corrections and comments on my attempts to write the introduction of my thesis. Sometimes his criticism was tough. It says, Harris, your writing is quite bad. My English is still quite bad. But that's what you expect from a father-like figure like him who tries to get the most out of his students. A part of his numerous major scientific contributions in relativistic astrophysics and his books, popularizing difficult aspects of physics in a unique way, Kip is also known for his involvement into science fiction movies, trying to drive our imagination to the extremes without violating the laws of physics, though. This is one of the pages of a handout he gave us in one of the weekly meetings to stimulate our brains and to trigger us to play with new ideas. It was about the appearance of a dodecahedron spacecraft traveling through a wormhole for the 1997 movie Contact, where Jodie Foster was starring. Kip was initially involved in the scientific part of the movie and came up with extremely bright ideas that unfortunately were never filmed. I could talk about Kip's unique personality for hours, but you came here to hear Kip talking and not me. So we'll end up my welcoming by reminding Kip that in 1992, his group wrote a prophetic paper about the last 3 minutes of coalescing binaries and their characteristics that could be measured by future detectors. About a quarter of a century later, this dream came true. Gravitational wave astronomy had commenced. Paraphrasing Newton, sometimes giants should stand on the shoulders of other giants to listen more clearly. Thank you, Kip, for your generosity. Actually, I feel privileged that I had the chance to study next to you and spend a fascinating period of my life around your world line. So, this is a t-shirt for you. I have my own.
Can you hear me? Thank you, Harish, for that fabulous introduction. I have to say that the reason, a very big part of why I was able to achieve through Ligo and other projects as much as I did achieve was because of the contributions of Harish and other students and postdocs who worked with me. Their own research, while they were with me, the sum total of it was considerably greater than my own research, and I have great pride in what they did while they were at Caltech working with me. So thank you, Harish, as a stand-in for all of my students and postdocs over all of those, something like 5 decades of being a mentor. So 1.3 billion years ago, in a galaxy far, far away, while here on Earth, multicelled life was just forming and spreading around the globe, there in that galaxy, there were 2 black holes. Could we turn the lights off, please? There were 2 black holes whose shadows you see here against a field of stars. And they orbited around and around each other, and the light from each star came in, and it went around the black holes a few times before coming to your eyes. And this is what you would have seen if you had been there. And you see these whirling patterns in the stars caused by gravitational lensing, the bending of light from the stars coming past the black holes to you. As they orbited around and around, the black holes emitted gravitational waves, ripples in the fabric of space and time that carried off energy and causing them to spiral together and move faster and faster until they finally collided in a great cataclysmic explosion, producing a giant burst of gravitational waves that went traveling out through the universe, into the, out of the galaxy in which the black holes lived, into the great reaches of intergalactic space, across intergalactic space, and finally, in 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals, the gravitational waves reached the outer edges of our Milky Way galaxy. You can turn the lights back up now. They traveled then for 50,000 years through the Milky Way galaxy until on 14 September 2015, they arrived at the Earth, touching the Earth first at the Antarctic Peninsula. They traveled up through the Earth unaffected by all the matter inside the Earth and emerged first at our LIGO gravitational wave detector in Livingston, Louisiana in North America, near New Orleans. And 7 milliseconds later, they arrived at the LIGO gravitational wave detector in Hanford, Washington. The gravitational waves stretched and squeezed the arms of these interferometers. So this arm was stretched and squeezed, that was squeezed and stretched. And those stretches and squeezes, which I will talk about, caused by the gravitational waves, were monitored with light, with laser light. And the signal then went into a computer, and the computer produced then output, the visual output that we could see. And I woke up that morning to an email from a friend saying, you go look on this internal LIGO website, there is a signal came in that we may have discovered a gravitational wave. Well, the signal was too good to be true, and I and everybody else was skeptical whether it was real. But after a struggle of about 5 months with the younger members of our team looking in great detail at all of the, how the internal behaviors of the LIGO gravitational wave detectors were, could see no sign of anything wrong with the detectors, finally concluded this was the real thing. And so our team then, of a 1,000-person LIGO collaboration, announced the discovery to the world on February 11, 2016, and it made front page headlines in all the major newspapers around the world. How did we get here? I want to tell you the story of what led up to this discovery, and then I want to describe what has happened since, and then I will describe what I expect to happen over the coming decades and indeed centuries. This is really a very exciting field that has a very long-term future, as I will describe. So this all began with Albert Einstein in 1916. He had formulated his general theory of relativity, his laws of gravity, which said that gravity is associated with warping time and space. He had formulated this just 1 year earlier. He used the equations of his theory of gravity to predict gravitational waves. And he said what a gravitational wave is the following. The gravitational wave travels perpendicular to the screen here. That gravitational wave will stretch and squeeze space. And we can watch the stretching and squeezing of space by laying out a set of particles that are just floating freely. This gravitational wave and these particles are out in interplanetary space where there's no gravity to perturb the particles. And as space is stretched and squeezed, those particles are stretched and squeezed just like that. So it's a stretch horizontally and a squeeze vertically, then a squeeze horizontally and a stretch vertically in a pattern that carries a lot of information, as I shall describe. So that was the prediction. But Einstein, in making this prediction, then went on to say in the paper, in the technical paper in which he wrote the prediction down, he basically said, these waves I find in my calculations are so weak that humans are likely never to be able to see them. Nevertheless, in the 1960s, 50 years later, Joseph Weber at the University of Maryland a young electrical engineer who was turning himself into a physicist. He had the courage to build a detector for gravitational waves. And the things that gave him the courage was that, first of all, we understood by then, 50 years after Einstein's prediction, we understood that there were sources of gravitational waves far stronger than Einstein had ever imagined in 1916. Black holes and neutron stars. And second, technology had changed. And with this changing technology, we now had lasers, we had computers, we had many new technologies and techniques that made possible types of gravitational wave detectors that Einstein never dreamed of. And so it was sensible to start such a search. I was much influenced by Joe Weber, whom I met at Princeton when he visited, and whom I went hiking with in the French Alps, discussing these things. Also by my PhD advisor, John Wheeler, who is a great guru from the theoretical end about black holes and neutron stars and gravitational waves. So in 1966, when I went to Caltech as a young professor, I started a theory group working on these phenomena, black holes, neutron stars, and gravitational waves. And one of the things that we focused on was trying to develop a vision for what you could do with gravitational waves if you could detect it. A vision for what we call gravitational wave astronomy. And so this is a technical paper that I published together with my student Bill Press in 1972, laying out the first version of this vision for gravitational wave astronomy. The thing that underlay this vision, the thing that made me so excited about gravitational waves, was the great contrast between electromagnetic waves, that is light, X-rays, radio waves, gamma rays, the kinds of radiation or waves that have been used until LIGO came to study the universe, and gravitational waves, the new kind of tool, new kind of way that we wanted to use to study the universe. Electromagnetic waves are oscillations of the electromagnetic field that propagate through space as time passes, whereas gravitational waves are oscillations of the very fabric of space and time itself. So radically different physical phenomena. Electromagnetic waves are, in astrophysics, incoherent, almost always incoherent superpositions of emission from individual particles and atoms and molecules, whereas gravitational waves are emitted by the coherent bulk motion of large amounts of mass and energy. So the emission process, completely different. Electromagnetic waves are all too easily absorbed and scattered by dust and other material between us and the source. Gravitational waves, as I told you, they penetrate through the Earth. They penetrate through everything. They're never significantly absorbed or scattered, not even if they are created in the birth of the universe and travel through the very hot, dense matter of the very young universe. With these huge differences, it seemed clear to me and my students and colleagues in the early 1970s that many sources of gravitational waves would never be seen electromagnetically. And that is the case thus far with colliding black holes, which was the first thing we saw. No electromagnetic emission has been seen from them as yet. No light, no X-rays, no gamma rays, no radio waves. Second, that many surprises are likely. Because you're looking at the universe in a whole new way, you're likely to see things that you were never able to predict. And correspondingly, then, there is a potential for gravitational wave astronomy to revolutionize our understanding of the universe. So this seemed so compelling to me in the early 1970s that I thought that if I could become convinced that the experimenters had a real chance, a good chance to detect gravitational waves, I would do everything that I could as a theorist, that I and my students could, to help the experimenters pull it off. Now, in this same year, 1972, Rainer Weiss, who had been a postdoc at Princeton when I was a graduate student, so I knew him from there. He was an experimenter, I was a theorist, but I sat in on the experimental group every week, the experimental group in which he was working, in order to really learn about experiment. Rainer Weiss had gone to MIT in 1972, the same year as I published with Bill Press this vision. He wrote a technical paper which he distributed to colleagues. He didn't publish it because he thought if you build a gravity wave detector, you shouldn't publish about it until you discover gravitational waves. So he would have waited nearly 50 years to publish this. but he wrote this technical paper, distributed it to us, in which he described a new type of gravitational wave detector called a gravitational wave interferometer. And the basic idea of this detector is the following. You're looking down on the detector. These blue things are mirrors that are hanging then from overhead supports, which is pointing out for you. A beam splitter sits light into two more mirrors there. You send a laser beam in, and it splits in two, and half of it goes down here, goes through a hole in that mirror, bounces back and forth many times, comes back to the beam splitter. Half of the light bounces off this beam splitter, goes through a hole in the mirror, bounces back and forth many times, and comes back, and the light then recombines here and goes toward a photodetector. Now, what happens is when these mirrors are pushed apart by the gravitational wave, they're hanging there and they're free to move back and forth at frequencies high compared to the swinging frequency of a pendulum. Then these mirrors are pushed apart. Then the light, then those mirrors are pushed together, so the light that goes into these arms travels farther than the light in those arms. There's an increase in the difference in the travel time. And so it turns out, for those who know about interference of light, that there will be a change in the intensity of the light that goes toward the photodetector as these two pieces of light from these two arms interfere. That's why we call it a gravitational wave interferometer. It is based on interference of light. So that was the basic idea. That's about as technical as I'm going to get in this lecture, but I wanted to lay it out for those who know a bit about this kind of optics. And now let me tell you what my reaction was to this. I looked at this, I did some numbers for myself, and I decided that Ray Weiss had either gone crazy, he'd become stupid, or something was wrong, because this didn't make any sense at all to me. And I was in the final stages, just a few weeks away from submitting for publication a textbook called Gravitation on the theory, Einstein's theory of relativity, together with my PhD advisor, John Wheeler and Charles Misner. And so I didn't have time to go talk to Ray. I just wrote down in this textbook, I described this idea briefly in the textbook just before we sent the book to the publisher. And I used a very mild phrase, this is not a promising approach. And let me explain to you why I thought it was not a promising approach. Let me give you some numbers. I was expecting that the strength of the waves would be one that stretched and squeezed these arms by 1 part in 10 to the 21. That's a 1 billionth of a trillion, a very, very tiny amount. That's the fractional change in length. If I multiply that then by the length of 4 kilometers, you get the mirrors moving back and forth by 10 to the minus 17 meters. Now let me just tell you just how small 10 to the minus 17 meters is. This is the magnitude of the motion of those mirrors. And even for a physicist, even for an experimental physicist, it's just good occasionally to go through these numbers, just to remind yourself how small this is. You begin with 1 centimeter. You divide by 100, you get the thickness of a human hair. You divide by 100 again, you get the wavelength of the light that's used to measure the motions of these mirrors. Divide by 10,000, you get the diameter of an atom. Divide by 100,000, you get the diameter of the nucleus of an atom. Divide by 100, you get the magnitude of the mirror motions. That's nearly 1 trillion times smaller than the wavelength of the light that you're claiming to use to measure the motions of these mirrors. That's crazy. Or at least I thought it was crazy. And then, over the next 2 years, or 3 years, I talked in depth with Ray Weiss. I talked in depth with a colleague in Russia, Vladimir Brzezinski, whom I will return to a little later. And I studied Ray's paper, and I did some additional calculations of my own, and I became convinced that this had a real possibility to succeed. And so I did make the decision that I would, that I and my research group would do everything we could to help Ray Weiss and his experimental colleagues succeed in detecting gravitational waves. So that's how I got into this. In parallel, Ray's idea had been learned about by a group led by Heinz Billing in Garching, Germany. I'm afraid we're losing a bit of this off the screen, but that was in Garching, Germany. Here you see the discrete spots made as the light goes around and bounces back and in an arm of the mirror. These are spots on the mirror. And so that group in Garking, a superb experimental group, built a prototype gravitational wave detector, much smaller than we would ultimately need, and got it working by 1975. By 1976, a group in Glasgow, Scotland, had also heard about Ray's ideas and started building a gravitational wave interferometer. This group led by Ronald Drever and Jim Huff. And that group, well, actually Ronald Drever, had a really brilliant idea for improving on Ray Weiss's gravity wave detector. They said, instead of making a hole in the mirror, in this mirror and sending the light through and bouncing it back and forth many times, you put a coating on this mirror so it's highly reflecting, and then it turns out if you separate these mirrors by a half integral number of wavelengths of light, the light will get sucked in here and it will bounce back and forth many times, and then it will leak back out. And you're only making one spot on the mirror, and this becomes much easier experimentally from that point of view, but much harder in other sorts of ways. But this was a brilliant idea. It was, the team did succeed in pulling this off, and this is the way the gravity wave detectors work. So based on that and several other key inventions that Ron Drever made, we brought him to Caltech to start an experimental gravity group. I worked, it wasn't hard. I convinced my colleagues at Caltech that we should start such an experimental group. We brought Ron Drever there to work on it. Brought Stan Whitcomb from the University of Chicago to work on it. Stan became the chief scientist of the Ligo Project several years later, the real lead in hands-on experimental work. And then in 1984, based on, somehow I lost the slide in here, so I need to tell you that at the same time as we were building a 4-meter prototype, Ray Weiss and his team at the MIT was completing a 1.5-meter prototype, a much smaller gravity wave detector, but more importantly, was carrying out a feasibility study to figure out all the things that could go wrong and how much it would cost to fix them if you tried to build a gravity wave detector like this, an interferometer with arms that are several kilometers in size. And so in 1984, based on that MIT feasibility study, based on the prototypes in Garking, Glasgow, MIT, and Caltech, Caltech and MIT got together and we created the Ligo Project. And from 84 to 87, it was run by three of us, by Ray Weiss, Ron Drever, and me. A troika, to use a Russian phrase. A Russian phrase that, in my mind, means a very dysfunctional leadership. And we were the most dysfunctional, the most incompetent leaders of any large project that I think the physics community has ever seen. And so inevitably, we threw up our hands in 1987, due in considerable measure to pressure from the National Science Foundation, from Caltech and from MIT. We got ourselves a real director to lead LIGO. Robbie Vogt, who had been the first chief scientist at the Jet Propulsion Laboratory that does all of this interplanetary space missions and is part of Caltech. So Robbie came on as the director, and he led us in 1989 in working out all the details, all the foundations for, and then writing a proposal to construct a LIGO, gravitational wave detectors, a proposal to the National Science Foundation. We said we would first build the facilities, then we would use a two-step strategy. We would build initial interferometers at a sensitivity where we would almost certainly not see anything. And then we would build advanced interferometers based on the knowledge and the experience we got from the initial interferometers. We would build advanced interferometers that would see a lot. And so that was the plan in 1989. That's what we said we would do. It took 3 years to get the funding to do this. We had great opposition from powerful members of the astronomy community who could not understand the idea that you go out and you build a gravitational wave detector for $300 million and you don't see anything. And so then you have to pay even more to build the second generation, and then you have success. But in fact, we were coming from the physics community where that was a reasonable way to proceed. And so that's the way we proceeded. And we did succeed then in convincing Congress as well as the National Science Foundation to fund us. And from 1992 onward, I have some pride in Congress, whether it's the Republicans or the Democrats in power. Congress backed us completely through a first generation of interferometers that saw nothing, and then a second generation which had success, just as we had said it would be. And it was, it didn't matter who was in power, the Republicans or the Democrats, they backed us, and both political parties took great pride in that when we saw our first gravitational wave signal. In 1994, we brought on a new director, Barry Barish, who had much more experience in running large projects than Robbie Vogt. Robbie probably had enough to get us through that first phase. Barry led us then in the construction of these facilities. He recognized that these detectors would be so complex that it would require a much larger team than we at Caltech and MIT could possibly put together alone. And so he expanded LIGO to a team that is now 1,000 scientists and engineers at, well, at 80 institutions in 16 nations. That's about what it was when we saw the first gravitational waves. It's now even larger than this. And he led that team in a very superb manner that resulted in his getting the Nobel Prize together with Weiss and me. In the year 2000 to 2010, then, under Barry's leadership, the team built the initial interferometers. They didn't see anything. They carried out the initial searches. And Barry was then stolen away from us by the high-energy physics community that needed a leader for their next really big project. And so we had a succession of two other leaders, Jay Marks and David Reitze, who are also superb. This kind of scientific leadership is absolutely crucial for success in this kind of a project. And we were very fortunate to have these great leaders. Then from 2010 to 2015, under Jay's and David's leadership, we built and installed the advanced interferometers. I'm going to pause there and return to talk about the first detection, but I need to tell you before I do that, the key second train of work that was required in order for the first detection of gravitational waves to really succeed was to understand the source of gravitational waves that we were going to see. And already in 1983, when we were initially planning LIGO, it seemed pretty clear to me that the first thing we would see would be colliding black holes. I won't go into the reasons, but I felt it was quite compelling that that was the first thing we would see. And we made estimates of how strong the waves would be at that time. We said 10 to the minus 21 for this strain, the fractional change in arm length. As the wave passes, that is precisely what the first signal was. So we really knew what we were doing. But we also had an uncertainty of that in that 10 to the minus 21 of a factor of 10. It could have been 3 times bigger or it could have been 3 times smaller, and we just didn't know in that wide range. And so I began to strongly encourage people who solved Einstein's equations on computers to push very hard to simulate through this process called numerical relativity, to simulate the orbital motion of two black holes around each other and their collisions and merger, including the effects of the spins of the black holes and the differing masses of the black holes. And I thought this was absolutely crucial for getting information out of the first signals that we would see, as it did indeed turned out to be. In the early 2000s, I became quite alarmed because there was nobody working among these numerical relativists who could simulate the orbital motion of two black holes around each other just once, much less simulate the spiraling together and collision. And so I left the LIGO project in the early 2000s, left day-to-day involvement in it, in order to start an effort at Caltech in these simulations. But I did this in collaboration with Saul Tucholsky, a former student of mine, who was by then at Cornell, and he was the very best person in numerical relativity in the world, I felt, and he was leading a very strong group. So I basically built a group at Caltech to help his group succeed. In 2005, one of our postdocs, Franz Pretorius, had the first successful simulation of the black holes going around each other, colliding and merging. And then by 2014, the simulations were mature enough that they could be used for to understand LIGO's first observation. So that's where we were, with the simulations coming in just barely in time to go hand in hand with the observations of gravitational waves from the instruments. And so there we were, September 14, 2015. The plan was to start the first gravitational wave search on September 17, 3 days later. The detectors were already operating, and they were being tuned. They're very complex. They were being prepared into this state, the form, the configuration that they would be in for the first gravitational wave search, the tuning that required a number of days. And the experimenters had all gone home for the night at both sites. We had the two sites, one in Louisiana, one in Hanford, Washington, and a signal came in. And we woke up the next morning, and there was the data prepared by the computer. The signal was there. Of course, we didn't know whether it was real or not, as I told you. But the signal came in, and David Wrightsey, our director, declared, "Our search has begun." It began when the first signal came in, and we will freeze the configuration of the detectors, and we will now continue the search. This was the first signal in the raw data. It was so strong that you could see it in the raw data. We didn't have to do a lot of data processing. The same signal at Livingston, Louisiana, and Hanford, Washington. And when the signal was cleaned up, you had the gray trace. What we're plotting up is the stretching of space, and down is the squeezing of space. So it's stretching, squeezing, stretching, squeezing along one of the arms. And the red is from the numerical relativity simulations by that Caltech-Cornell collaboration called the SXS collaboration. And but we had to adjust in the simulations the masses of the black holes and the distance to the source in order to be able to get this very good match between the observations and the simulations. And so after that tuning of the simulations, we concluded that the initial black holes weighed 29 times what the sun weighs and 36 times what the sun weighs, total of 65 solar masses. The final black hole was 62 solar masses. So 3 solar masses had disappeared, had gone into gravitational waves. It's as though you had annihilated 3 suns and turned all of the mass of those 3 suns into energy and put all that energy into gravitational waves. That's what happened when these black holes collided. And it happened so fast, in about 1/10 of a second, that the power output, the energy per unit time, was 50 times larger than the power output from all of the stars in the universe put together. 50 universe powers, 50 universe luminosities, for a brief period of 1/10 of a second, coming off in gravitational waves. Just the largest explosion that humans had ever had any evidence of, except the Big Bang birth of the universe. That's what we saw. And it moved the mirrors back and forth by this tiny amount of 1/100th the diameter of the nucleus of an atom, even though that's how much power was in the signal. We carried out 2 gravitational wave searches. Between each search, we then went in, and I should say the experimental team. I was no longer very much involved with this because I'd gone off to help the numerical relativists. But the team carried out 2 gravitational wave searches between 2015 and August of 2017. And in those 2 gravitational wave searches saw 10 black hole collisions. And these are simulations of the 10 black hole collisions. You see big black holes, you see little black holes. You see them going around and around and ultimately colliding and merging. And we were able to determine the direction of the source on the sky by the delay in arrival of a piece of the signal at the 2 locations at Hanford, Washington, and Livingston, Louisiana. I told you the signal first arrived in Livingston and then in Hanford, 7 milliseconds later. Livingston is south of Hanford, so the signal came from the south, and that's how we knew it first touched down somewhere around the Antarctic Peninsula. But that told us only the north-south direction for where the source was. East-west, we didn't have a very good sense of the direction. So these were the uncertainty error boxes on the sky of where those first few gravitational wave signals were. They weren't very good. But then a new third gravitational wave detector began to operate, a new third advanced gravitational wave detector built by the Virgo team I guess this is supposed to be 19 labs and 250 plus scientists in France, Italy, Netherlands, Poland, and Hungary. And with 3 gravitational wave detectors, we could then triangulate and get good directionality in the east-west direction as well as north-south. And so on August 14 of 2017, a signal came in. It was a colliding black holes, and the location on the sky was this little tiny region. Well, it's not that so tiny. It's somewhat larger than the moon, but still that's pretty small compared to what we were having for angular resolution on the sky. So this was very exciting. We could now tell the electromagnetic astronomers where to look to see if they saw any X-rays or light or radio waves coming from our sources. Then, just a few days later, we saw gravitational waves from what turned out to be the collision of 2 neutron stars. Each of these neutron stars had a diameter of about 20 kilometers, and yet had the mass of about 1.5 times the mass of the sun. At the center of the neutron stars, the density was 10 times higher than the density of the nucleus of an atom. And these stars orbited around and around each other, emitting gravitational waves and gradually spiraling together. And as they spiraled together, ultimately they collided and they produced a gigantic fireball of hot atomic nucleus matter exploding out into space and emitting every form of radiation known to humans. This fireball was initially so dense that it was very hard for radiation to get out. And as it expanded, it became easier for radiation to get out. And the first thing that came out was the highest energy type of radiation there is, gamma rays. Then a little bit later, X-rays. Then ultraviolet. Then light. Then ultimately radio waves. This was what theorists had hypothesized these things occurred. They called them kilonova, and we saw them. These were the gravitational waves that I'm not going to talk about, a particular way of discussing the gravitational wave signal. But the key thing is that 1.7 seconds after the 2 neutron stars collided, there was a burst of gamma rays seen by 2 different gamma ray telescopes that were in orbit above the Earth. And the best of the gamma ray telescopes, the Fermi telescope, said on the sky the location of the gamma rays came from was this big circle. But LIGO and Virgo together said the gravitational waves were coming from that tiny region. An hour or so later, X-rays came in, then ultraviolet, optical, infrared, and radio, and those you could see get very good angular resolution. You could see just where the source was, and it was in a galaxy that sat right here inside the LIGO and Virgo error boxes on the sky. We call this multi-messenger astronomy. Each messenger is a particular form of radiation, gravitational waves, X-rays, gamma rays, radio waves. And this was the beginning of multi-messenger astronomy, and it is becoming a very big thing in astronomy now as the years go by. And one of the very interesting things that came out of this was by looking at the electromagnetic waves, particularly the light, it was possible for the astronomers to deduce that a huge amount of gold and platinum was created in the collision of these 2 stars. So much gold and platinum that when you looked at how many such collisions are probably occurring in the universe, you could conclude that most of the gold and platinum in the entire universe, including all that is here in this room, was produced by those kinds of neutron star collisions. This is a conclusion that comes then from multi-messenger astronomy. Oh, and let me make one more remark about this. This is the most studied event in the history of astronomy. Something like 15 or 20% of the world's astronomers study this with one type of telescope or another. And it was just so exciting for the entire world of astronomy. It was a bigger deal even our first gravitational wave detection from that point of view. It's a beginning of a whole new way to do astronomy. We began our third gravitational wave search on April 1st of this year with improved detectors. Each time we shut down, the team worked to improve the detectors, bringing them toward their design sensitivity. We began on April 1st. There is a smartphone app that you can get for your smartphone. It's called GW Events, or Gravitational Wave Events. That smartphone app that is produced by the LIGO Virgo team together is one on which you will get the information about every gravitational wave signal that is detected within minutes of when it is detected. The information goes on there, and the world's electromagnetic astronomers and neutrino astronomers, they look at their iPhone app, and when there's a detection and the information about where it is on the sky and how far away it is from Earth is right there, they'll go turn their own types of telescopes toward the sky and look for that, see if they could see radio waves or light or X-rays from it. And then they put onto the app their observations as soon as they've made their observations. And so the data come through very quickly after each gravitational wave detection. This is just since April 1st. And I'm going to show you what this looked like then inside this app as of yesterday. And you probably can't see the details here, but these are various gravitational wave events in here. Everything that begins with GW is a gravitational wave event. And the important point is that in the past 10 days, there have been 5 collisions of black holes. 5 in 10 days. Remember, I told you that there were a total of, I think it was 10 or 11 in the first 2 searches, 5 in the last 10 days. And about 4 weeks ago, there was our second neutron star collision. The problem with that neutron star collision is one of our 3 detectors was not operating. So we couldn't say very well at the time. The astronomers have been having trouble pinpointing it for lack of that third detector. So it shows you how important the third detector is. This is really exciting. And you can also set the app up so that it will make a chirp, go whoop, every time a signal comes in. And so you can sit there with it in your pocket, as my granddaughter does, and waits for a signal to come in, and whoop, and then go look quickly and see what it was. Let me just give you a little bit of sense of these advanced LIGO gravitational wave detectors. I'm going to show you some photos. This is a photo of one of our detectors at Hanford, Washington, seen from the air. I showed that before at the very beginning in my story of the first detection. Down inside the corner building, there are these vacuum tanks. It's all vacuum inside this big tank. And inside this tank hangs one of the mirrors. Inside that tank hangs another mirror. Inside that tank is this beam splitter that splits the laser beam in 2. And Barry Barish, who made this this slide for me, he puts an American baseball player here just to show you the size of this. He didn't want to put a LIGO scientist there. He thought it would be more interesting to put a baseball player there. But it gives you some sense of the size of this apparatus that is housing inside, it's housing the gravitational wave detector. This is one of the mirrors hanging from overhead support. It's hanging by a quartz fiber, a fused silica fiber, and it's free to swing as the gravitational wave pushes it. It doesn't look like it's free to swing, but all this apparatus around it is basically, among other things, protecting it. If the wire breaks, the fiber breaks, you don't want it to fall on the floor and get damaged. And so it will get caught if the fiber breaks, for example. Okay. A key thing about these detectors is that on each of these detectors, each of these interferometers, coming out of it is 100,000 data channels. One of those carries the gravitational wave signal. And all the rest are carrying information about the things that could go wrong inside this gravitational wave detector, or things that are going on in the environment around it. And the key thing is that if you have a signal, you go in and you look at many of these data channels to see if something was going wrong. And the young experimenters, they really know what data channels to look at to see if something was going wrong when a signal comes in. But that indicates the complexity of it. And why is it so complex? That goes back to my very first slide about Ray Weiss's invention of this scheme. I didn't think it was possible because these motions are so tiny And there are so many things that can go wrong when you're trying to measure motions that are that very, very, very small. And this superb LIGO team has developed techniques to remove or to prevent all of these things from going wrong. But it takes a huge number of different techniques and therefore a huge number of data channels to tell you about what's happening. I want to talk about one other aspect of advanced LIGO that I find particularly interesting, and in fact it occupied my own research group for several decades, still does. If I have advanced LIGO here, I have the two mirrors that are have a laser beam bouncing back and forth between them, and we're measuring the gravitational wave strain, the fractional change in their separation. And in advanced LIGO, not today, but in about 2 years, when it's fully at its design sensitivity, it's not yet working perfectly, we'll be monitoring the motions of these mirrors to a precision of 10 to the minus 19 meters. And that turns out to be the precision at the level at which these mirrors' positions are fluctuating due to quantum mechanics. Now let me explain in a little bit more detail what that means. Inside an atom, there are electrons, and the electrons' locations are continually fluctuating wildly. You have only a probability distribution for where those electrons are located. You can't say where an electron is now. You can only say what's the probability that it's here or there or there. Those fluctuations are a level of something like 10 to the minus 10 meters, the size of the atom. And the advanced LIGO mirrors are much heavier than the electron, and great effort has been made by the experimenters to guarantee that the laser light is measuring only the motion of the center of mass of the mirror, that is the average location of all the atoms in the mirror, and isn't measuring anything else. So the mirror, as far as LIGO is concerned, is a particle that weighs 40 kilograms. Because it's so much heavier, the random motions, due to this quantum mechanics business, random motions are much, much smaller than the random motions of an electron in an atom. But they're big enough that they're at the level of the noise in advanced LIGO. They are a major contributor to the noise in advanced LIGO. And as we go beyond advanced LIGO to the next generation, which I'll talk about in just a minute, as we go beyond advanced LIGO, it is going to be necessary to make measurements of gravitational waves at a level that is smaller than the random motion of the mirrors, these quantum mechanical mirrors, the random motion of these 40-kilogram particles. How do you do it? Vladimir Berginsky, my dear friend in Moscow, already in 1968, think how long ago that is. That's 50 years ago. He realized that this problem was going to arise with gravitational wave detectors, and he said, you've got to worry about it. He invented a name for the technology that we would need in order to deal with this. This just says, for the first time, humans will see human-sized objects behave quantum mechanically. That's what's going on here. And he invented a name he called, something's going wrong. We're losing the bottom of the slide off. Everything has been pushed down. Is there some way with the projector to raise it all back up? Thank you. So he invented the name quantum non-demolition for a new technology that was required to deal with this. You want to be able to get the gravitational wave signal through a randomly quantum mechanically jiggling 40-kilogram particle without those quantum motions demolishing the signal. So quantum non-demolition technology. This is now a branch of what is called quantum information science, which includes quantum cryptography, quantum computing, and so forth, quantum communication. And quantum non-demolition is our branch of that, and we use many of the same techniques as are used in other areas of quantum